All right, Module 2. Nope, Module 2, which is Unit 2. It's Chapter 3, Lesson 1. I can find a unit rate. Basically, from here until middle of the second trimester, we are going to be discussing, analyzing, graphing, ratios, proportions, constant of proportionalities, percents for the next couple months, or not a couple months, probably a month and a half. So the first thing we're going to lead off with is I can find a unit rate. One of the most basic things ever. What is a unit rate? Rob, you know?
It's like one.
Yeah. Yeah, when you think of unit rate, per one. 50 miles per hour. Negative 30 feet per minute. Six winds per season. $12 green M&Ms per package. 36 cents per ounce. $1.05 per bottle. These are all considered unit rates. And the reason why they're considered unit rates, well, they're considered units because we have units here. We have miles and hours, feet and minute, winds and season, green M&Ms and packages, money and ounces, money bottle. So there's the unit. And then the reason why it's called unit rate is because the rate is per one. One. Which means you need to have the number 1 in the denominator. Mr. Thomas can type 540 words in 4 minutes. How many words? Well, we should just put what is the average rate of words per minute? Mr. Thomas can type 540 words in 4 minutes. What is the average rate of words per minute? So what we would do is we would take the 540 words, divide that by 4 minutes, and when you type it into your calculator, you will get 135 words per minute. Nico, why do you have your phone out? Why is it on? Okay, good. So on Saturday, we all know it was Saturday, I ordered 240 slices of pizza. True story.
For the amount of calls and arrestment.
Yeah.
The amount of calls.
Sure, yeah, no kidding. And I had 30 people over my house. So how many slices of pizza did each person get? Well, you take your calculator, which you probably don't need, but you would do 240 divided by 30, which is what, Jack? 8 slices per person. Now, these unit rates, like doing these very, very simple, and where do they really appear in real life? Quite often. Better buy. Which is the better buy? All right, this is really putting this unit rate stuff to application work, application purposes. Which is the better buy? So which one of these is truly the better buy? Which one are you going to buy? A 12-pack of Pepsi that costs $6.99 or an 8-pack of Pepsi that costs $4.49? Now, your answer cannot be neither. I don't drink Pepsi, I drink Coke. Okay? I've had people, try to be smart about that, or I don't drink soda, I just drink water. Jack?
The 8-pack?
How do you know it's going to be the 8-pack?
Well, I kind of just did it like 12 times 2 to get to 24, then 8 times 3 to get to 24. So then I just did whenever I multiplied it by, I did 2 times 6, 99, and then 3 times 4.
Okay. Well, 2 times 6 is 12, 3 times 4 is 12. Okay. So we maybe could round this up to $7 and multiply that by 2. Now, for those of you that have no idea what Jack was talking about, he said the least common multiple of 12 and 8 is 24. So he said, well, to get to 24, I would multiply this by 2. And if this is $7, 7 times 2 is 14. Good job. 8 times 3 is 24. So 449 times 3 is right around $13. So obviously this would be the better buy. And you can do that. That's one method. Drake?
What I did is I just took what the package originally, and then I divided it by the whole dollar, and then that would be that simple. Well, on the 8-pack, it's actually less change-wise, which equals out to be lower than the 99 cents compared to 12.
Okay. All right. That's good. Anything else? Mathematically, this is how you would set this up. Okay, if you couldn't decipher which one was the better buy. Mathematically, you would take the $6.99 and divide it by 12 cans. Or 12 bottles, whatever it is. And you would get 58 cents per bottle. The 8-pack, which costs $4.49, divide that by the 8 cans, and you would get right around 56 cents per bottle. So it's not much cheaper. You're only saving 2 cents. You take the 12-pack. Yeah, but you can buy another 8-pack and it'd be cheaper.
3 8-packs and 2 12, so you have to take them out.
Mm-hmm. Where it really starts to get tricky, and obviously I'm not going to throw this at you right now since this is our first time looking at this. I'm going to give you the same scenario, and what I'm going to say to you is this. The 12-pack is 12-ounce cans. The 8-pack is 24-ounce, or vice versa. Now which one's the better buy? Okay? And that's going to be later on this week. But for right now, this is what's going on. a coffee house sold 180 liters of coffee and used 30 liters of cream. What was the average rate of cream used per liter of coffee? Now, it is very, very easy for someone to whisper out right now the number 6. Okay? And then I would have to stop and say, stop being a robot. Because you guys keep doing and doing the same types of problems. You're like, oh, I got this. This is super easy. 180 divided by 30 is 6. This is super easy. I'm ready for the test today. Read the problem. The problem doesn't say the number of liters of coffee per cream. The question, what I want to know, is what was the rate of cream used per coffee? And if you're going to use 6 of these cups, 6 of these, this is a liter. If you are going to use 6 of these full of cream to 1 of these full of coffee, diabetes. Hello?
Diabetes in a cup.
Hi. Yeah, it's next hour. We are next hour. All right. That's all right. You're welcome. Bye. That's a ton of cream for your coffee. No one's going to take, give me one of those and then put about 6 of these cream. That's not going to happen. That's not going to happen. So we need to make sure not only are we setting up the problem correctly, but does our answer make sense? I have a question that I often ask about sugar per 1 cookie. And I will have people reverse it and say 32 tablespoons of sugar in 1 cookie instead of 1/32 of a tablespoon of sugar. Think about 1 cookie and 32 tablespoons. You would have this big old pile of sugar. And somewhere underneath there is going to be a cookie. And you're just going to... Now that's a diabetic coma. You ain't probably waking up from that. So we have to input the appropriate ratio. So our ratio is cream to coffee. And once we identify the appropriate ratio, we need to make sure that we input the appropriate corresponding value. And now we can reduce. And we will get 1/6 liters of cream per 1 liter of coffee, which makes way more sense. Here's a liter, here's a 1/6. Okay, that's about right. All right, maybe some people have parents that might be a little bit more than a 1/6. Okay, but this is comprehensible. That makes sense. Yes, Drake.
My stepmother has no creamer in her coffee.
Well, that's not good. All right, so I created a table here, and I'm asking you now to find the unit rate. That's a 3, 4, 5, 6, 210, 280, 350, 420. The first row of every table is always the x axis. The second row is the y axis. We always write our unit rate y depends on x. The number of miles traveled depends on how many hours we're driving. Correct? The distance traveled depends on how long we are traveling for. So in every single table, the first row is the x-axis, the second row is the y-axis, and when we talk about x and y-axis, I am actually talking about a coordinate plane, x-axis, y-axis, and the y variable depends on the x variable. That's why it is written y divided by x. Always. There is no exception. Y divided by x because the y depends on x. The number that I get in this table depends on the number for the x table. And it doesn't matter which one of these I choose, whether I choose to do 210 divided by 3, 280 divided by 4, 350 divided by 5, or 420 divided by 6. Every single one of these answers is going to give me 70 miles per hour. So what we have here is just a brushing of the surface of unit rates. I have a very, very simple 10-question worksheet that you are going to work on today in class with a partner. You should get it done before you leave.